So how was the quiz?
Yes, ma'am, it went well.
Okay. What about the others? How was the quiz?
Ma'am, it was nice.
Okay. It was easier than quiz 1, quiz 2, or
Ma'am, it was easier than quiz 1, but not from quiz 2.
yeah, quiz 2 the topics were very simple, right?
Yes,
So,
ma'am.
yeah.
Ma'am, before starting this, can I ask my one doubt from activity?
Yeah, which one?
Ma'am, activity 10.1, question number 6.
Okay. What's the question?
Ma'am, it is asking which is a vector valued multivariable function.
Okay. Okay, give me a second. I'll just open my. What is the problem in that? What are the options? Can you hear me?
Yes, ma'am.
Yeah. So, what are the options in there?
Ma'am, the option is fx comma y equals to 1 by 3 pi, and ex square plus y square, e to the power x square plus y square.
Okay.
And the other one is fx comma y equals to x cube comma y square.
Okay.
The next
Yeah.
one is
Yeah, I've opened it. Okay. So, what is the problem in that? What is a multivariable vector valued function?
ma'am, for vector valued we have to check from Rn to Rm such that m comma n is greater than 1. And
Yeah.
for multivariable function, same is Rn to Rm, but here m can be anything, any real number, but
Hmm.
the limitation is for condition is for n, that n should be
Hmm.
greater than 1. So,
Hmm.
ma'am, for this, for vector valued multivariable function, both conditions should be satisfied. That is for a
Hmm.
vector valued and for a multivariable function.
Hmm.
Ma'am, here if we are looking at option 1, we see
Hmm.
that it is going from R2 to R1.
Yeah.
From R2 to R1 means n is greater than 1, and n is greater than 1, so both of the condition for n is satisfied, that is multivariable and vector valued. But for n, um, for vector valued function, n should also be greater than 1, but here n is 1,
Okay.
so
Yeah.
it can't be a multivariable vector valued function.
Yes.
uh, and ma'am, for the I think there are only two multivariable vector valued function, the second option and the third option.
What about this one? X plus 1, x minus 1, and
Ma'am, here fx equals to x plus 1 and x minus 1. Here it is going from R to R
okay.
square.
Yes. Yeah, it's multivariable. So f of x, this option is not true.
Yeah.
But the last option is true, right?
uh, yes, ma'am, yes, the last one is
Yeah.
also true.
Yeah. So it should be 3. The answer should be 3, I guess.
Ma'am, here
This
the
one.
answer was 4.
Yeah. So yeah, because it's multivariable, f of x, this is not acceptable.
Not
Um,
because of multivariable, I think for because of vector valued function, because m and n both should be greater than 1 in vector valued, but for multivariable function n should be greater than 1 and m can be any number.
okay. Shall I discuss the concept so that it will be clear?
Ma'am, here the answer is 3 now.
Yeah, it should be 3.
Yeah,
But the
okay.
reasoning that you're giving for f of x is equal to x plus 1, x minus 1, I don't know what exactly you're telling, but yeah.
Ma'am, actually I am trying to say that here n
It
is
is
1.
it is vector valued,
Yeah,
but
yeah.
it is not multivariable.
But ma'am, it is not vector valued. No, see, n is 1. N is 1. And here for vector
No,
valued function, m
one
comma n
thing,
should.
I don't know what n and m are. So n is related to codomain or domain.
Ma'am, n is related to domain.
Okay, it is
Domain
1.
is one,
Yes.
yeah. And for vector valued function, domain and codomain both should be greater than one. But for
Hmm.
multivariable function, only the domain needs to be greater than one, and codomain can be any real number.
Yeah.
Now, I
So
think
this
here
is not
this thing,
multivariable, right? Because the
yeah,
domain is from R.
yeah.
Yeah. Yeah. So the answer will be 3 in this case.
Okay, ma'am, just this was the doubt. Okay, ma'am, you
Yeah.
can proceed now. Thank you, ma'am.
Okay. Okay, so yeah, till now, what we were dealing with is functions of one variable. That is, we were dealing with f of x. Um so the function f was dependent on one variable x. But from this week onwards, that is from week 10 content onwards, we'll be dealing with multivariable functions. That is, the function will depend on more than one variable. So a multivariable function is a function which depends on more than one variable. So if I have f of x comma y or f of x comma y comma z, it means that the function depends on the variables x, y, z. Or if I have f of x comma y, then it means that the function depends on two variables x and y. So in this case, the function is said to be multivariable. That is because it is depending on multiple variables, not just one variable. So in that case, you say that the function is multivariable. So then the multivariable function is divided into two categories: scalar valued and vector valued. So when I say f of x is equal to x squared, then the value of x under the map f is x squared, right? Yes.
Yes, ma'am.
Yeah. So when you talk about the value of a function, you're talking about what is happening in the codomain, right? And the function depends on certain value. So that is the variables on which it depends is about the domain, and the value that it takes is about the codomain, right?
Yes, ma'am.
Yeah. So when I have f of x is equal to x squared, f is actually a function from R to R. Agree?
Yes, ma'am.
Yeah. Just give me a second. Okay. Yeah. So now, when we talk about multivariable functions, it means that the function depends on more than one variable. So the domain should be a map, or the domain of the function should be in the form Rn, where this n is greater than 1. Does it make sense why it is called multivariable?
Yes, ma'am.
Yeah. So when the domain, the dimension of the domain is greater than 1, then the function is said to be multivariable because the function depends on more than one variable. Now, when we talk about the codomain, we are actually looking at the value the function takes. So that is when you have two categories: scalar valued and vector valued. So when do you say a function is scalar valued? When the output of the function is a scalar, right? And by scalars, we mean real numbers, right?
Yes, ma'am.
Yes, ma'am.
Yeah. So when the output is a real number, that is when the codomain is just R, you say that the function is said to be scalar value. And multivariable, this multivariable thing is based on what the domain is, and the scalar valued or vector valued is based on what the codomain is. So when it is scalar valued, it means that the output is a scalar, that is, it is a real number, which means that the codomain is R. It is said to be vector valued if the output is a vector. And by vector, a vector in R2 is represented by two coordinates, right? X comma y. Yes.
Yes, ma'am.
And any element of R2, we call it as a vector, right? Or R3, we call those also as vectors. So because we can
Yes, ma'am.
represent it as vectors. So when it is vector valued, if it is an element of R2, R3, etc. So in that case, the function's codomain is Rm, where this m is greater than 1. So now there is no confusion of why, whether n has to be greater than 1, m has to be greater than 1, nothing, right? It is clear that if it's scalar valued, then the output is a scalar, and if it is vector valued, then the output is a vector, right?
Yes, ma'am.
Is it clear to everyone? And because of it being a multivariable function, the domain has to be, the domain has to
Greater than
depend,
1.
yeah, the dimension of the domain, yes. So the function has to depend on multiple variables, right? Okay. So these are scalar valued multivariable functions and vector valued multivariable functions.
But
Ma'am,
not the
just
codomain, ma'am.
For what?
But domain will be the multivariable, but not the codomain, ma'am. We will not be considering codomain, you mean to say?
No, I mean the multivariable. The term multivariable is because there are multiple variables the function
In
is
domain
depending.
itself, not in
Yeah,
codomain.
yeah. So this is domain, and the scalar valued and vector valued refer to the dimension of the codomain. That's why this valued.
Okay.
What is the output? That is the concept.
a
Right?
quick. So how different is this from transformation, linear transformation?
You can think of as a linear transformation as a multivariable function. That's it.
It's a type of multivariable function, is it?
Yeah.
Linear
It's a
transformation is it?
yeah, linear transformations are also functions, right? It's just that they are special because we talk about them as functions between vector spaces and all that. So
Right.
I agree that every linear transformation can also be seen as a multivariable function. Okay, it depends. If you have t from R to R, then this is going to be a single variable, single valued function.
Right.
But if I have, say, R2 to R2, then this is going to be a vector valued multivariable function.
Right. Right. Okay.
Ma'am, a very basic question. I am not very sure though. Why do we write this way? That a function is defined from D to Rn, where D is a domain in Rn. Why cannot we write in this that it is a function from Rn to Rm? Is there some mathematical concept behind the way
Yes.
that we are writing it in such a way?
Yes. So if I define the function, I'll take one variable function, f from R to R, where f of x is equal to 1 by x. Is this function even well defined throughout R?
No, it breaks
No.
at x is equal to 0.
Yeah. So there is a problem. There is some point in the domain where there is a problem. So at that
Yeah.
point, the function is not defined. So I have to write this function as R minus 0 to R, right? So this is the D. So we are collecting the set of all points where the function
Okay.
is defined.
Is defined. I see. Okay. And that's where we define that D is a domain in Rn.
Yeah,
As per
exactly.
the definition of domain then. Okay, ma'am. Thank you.
Yeah.
Thank you very much.
Okay. So yeah, this simple question of which of the following are scalar valued and vector valued? Are they all multivariable functions?
Yes, ma'am.
Yes, because f depends on more than one
More than
variable
one
in each
variable.
of the cases. Yes. So all of these are multivariable functions. Which of these are scalar valued? Which of these are vector valued? So is the first one scalar valued or vector valued?
Scalar
Vector
value.
value, ma'am.
Why is it vector valued?
Scalar scale. It's only single value. It returns a,
Yeah.
returns a real
The one
number.
who said vector valued, why is it vector valued? Why did you say it is vector valued?
Because we'll be getting for x and y, we'll be getting some unit vectors, no, ma'am. So we are just multiplying to, okay, dot product
No.
or some.
What is f of 1 comma 1? Or say f of 1 comma 0? What is this?
1 plus sign 1 means
1 into 0 plus sine of 1 into 0, right?
yes, ma'am. Oh, yes,
So what is this answer?
1.
0, right? Because this product is also
Oh,
0.
0. Yeah,
Sine 0.
correct, ma'am.
Yeah. So the output is a real number, right?
Yes, ma'am.
So it's a
Oh,
scalar
right.
valued. Yeah.
Correct, ma'am.
So it's scalar valued. What about the second one?
Scalar.
Scalar.
Yeah, because the output is going to be a number. The third one?
Vector.
Yeah, Why? Because the output is a vector with 3 components. So the
Yes, ma'am.
codomain of this function is R3. What about option 4?
Again vector.
What is the codomain?
R square.
Yeah, it's R2. For the fourth option, the codomain is R2, so it is a vector valued function. What about option 5?
Scalar.
Scalar.
Scalar, because it's going to give us a real number as output. So
Ma'am,
it's a scalar value.
if you take the option 1 and option 5 kind of thing, according to xy, which you have taken f of 1, 0, the same will be in option 5 also, no, ma'am, xy.
Yes, f of 1 comma 0 is going to be 1 into 0, which is 0, which is a real number, not a vector, right?
Right, thank you.
Yeah. So if it is a vector, you will have components like this. You will write it in a bracket with separating it with commas. Then you say it is a vector, right?
Yes, ma'am.
Yeah. So this is the difference between scalar valued and vector valued. But these are all multivariable functions because the function depends on more than one variable. So in this way, we have two different types of multivariable functions. One is scalar valued multivariable functions. The other is vector valued multivariable functions. Okay. So yeah, this is one of the questions. And you know how to add two multivariable functions, subtract two multivariable functions and all that, right? Suppose I have f from R2 to R3 and g from R2 to R5. Can I add f and g?
No, ma'am.
No.
The
No,
dimension should be
because
same.
because the addition is actually defined component wise, right? This is defined as f of, okay, yeah. So because f is a function which takes to R3, f of x comma y. Okay, this is going to be equal to f of x comma y plus g of x comma y. This will have 3 components, this will have 5 components. So I cannot add those two, right? Yes?
Yeah.
Correct, ma'am.
So I cannot add functions of this type. But if it is R3 and R3, then I'll add component wise. Just like how we add two vectors in R3, we just add it component wise. And that way the sum will be well defined. Okay, so similarly subtraction and scalar multiplication. Because you have already seen a vector space, right? And in a vector space, you add, you do scalar multiplication and all that, right? Have you ever
Yes, ma'am.
multiplied two vectors?
No.
Dot product and
Okay. Dot product is different. Okay. But in general, you haven't multiplied two vectors, right?
No.
How
yes,
will you
ma'am.
multiply 1, 2, 3, and 4, 5, 6? Yeah. Okay. If you define multiplication to be the dot product, then it makes sense. But there are multiple ways. Like there is no usual multiplication that is defined for vectors, right?
Correct, ma'am.
Yeah.
Unless and
Yeah.
otherwise it is given in a function kind of thing.
Yeah. So we know how to add vectors and we know how to do scalar multiplication of the vectors. Okay, so with that in mind, let's answer this question. I have D, which is a subset of Rn, and I have F and G, both from D to Rm. So are these multivariable? Let's assume n is greater than 1. Are these multivariable functions?
Yes.
Are they vector valued or scalar valued? Let's take m to be
Vector
greater than 1.
Yeah, vector valued.
Yeah, if m is equal to 1, they are scalar valued, but if m is greater than 1, they'll be vector valued. Okay, so option 2, let's directly go to option 2. The sum of f and g is given by this. Is it right? F plus g of x is f of x plus g of x.
Yeah.
Yes,
It
ma'am.
Yeah,
is.
so that's how we add two vectors. If I have, okay, yeah. In general, any two functions also you add like that only, right? Even if it is from R to R, that's how you add it, f of x plus g of x. The same way, yeah.
Ma'am, it's just written f of x, right?
Yeah, x
So
tilde.
why are we saying, oh, x tilde? Okay, then it becomes a vector. Okay, fine. It
Yeah.
was just appearing as x, and that was my question. Why it is a multivariable? Okay, fine. As long as it is a tilde, it is fine. Okay, fine.
Yeah. So X belongs to D, which is a subset of Rn. Here we have taken N to be greater than 1. It's already given multivariable, so it's assumed that N is greater than 1, right? Otherwise, it wouldn't be multivariable.
Yeah. Okay.
Yeah. Okay. So what is option 3? When I have a scalar, the function CF is defined by what?
C of fx, f of x, C into
Yeah.
f of x.
So the scalar multiplication that we do is CF of x. The function CF of x, okay, x tilde is going to be equal to C times f of x tilde. So this is not right. Not 1 by C. It should have been C, right?
Yeah.
Yes, ma'am.
Okay. So now let's
Yes.
get to option 1. The product function f into g is defined by this. Is it right? F of x into g of x.
It's not right because multiplication doesn't work.
Yeah, exactly. What is f of x? F of x is a vector, right? It's a vector in Rm, right? F of x belongs to Rm. Similarly, g of x belongs to Rm. Yes or no?
Yes, ma'am.
So I don't know how to multiply two vectors. Product of two vectors is not known. So the product function fg is not defined this way. In fact, you cannot even talk about product of vector valued functions because for the fact that you don't know how to multiply vectors. Okay, and option 4 says if m is equal to 1. If m is equal to 1, what are f and g?
Scalar valued
I'm
function.
sorry. Sorry to interrupt.
Yeah.
Maybe not associated with this. When you say that we don't know how to multiply, is it that it just doesn't exist, or it is not part of this particular course and we have not been taught, or it
No,
just
it
doesn't
doesn't exist.
exist? It
Yeah.
doesn't
If I
exist.
take
Okay, fine.
yeah, if I take two vectors in R2, say this, how will I multiply these two vectors? Do you
Yeah, I
know how
mean,
to
it's
multiply?
no, we don't
No,
know,
right?
but it just
Ah,
doesn't exist in the mathematics world. It doesn't exist, right?
yes, yes, yes.
Fine. Okay.
Like you can, I will say that for me, multiplication is defined as dot product, I can say. Or I can say that it is
Okay.
defined as 1 into 0 plus 2 into 2. That's my definition. So,
We can define anyways, and then perhaps it can
yeah,
be applicable, but there is no universal way of multiplying.
defining. Yes.
Yeah, fine. Okay, ma'am. Thank you.
Okay. So when m is equal to 1, because the codomain is R, f and g will be scalar valued functions, right?
Yes, ma'am.
And now can I multiply these two functions?
Yes, ma'am. Possibly.
You can always, right? Because the output is a scalar.
Yes, ma'am.
Yeah. So in this case, you can multiply. And can I divide in this case?
Yes, ma'am. We would
Yeah.
get two scalars.
Yeah, because we know how to divide two scalars. We can do this as long as g tilde is not 0, right?
Yes.
Yes, ma'am.
G of x tilde is not 0. So yeah, that's what is option 4. If m is equal to 1, then we have scalar valued functions. And when g of x tilde is not 0, then f by g is defined as f of x tilde by g of x tilde. So this is right. So we know how to add scalar multiply, like multiply a function with a scalar. So these two we know, but there is nothing that we know about multiplication, division and all that. But we can still do multiplication and division if they are scalar valued functions. Okay, so that is what this question deals with. Um, okay, so first tell me, what is the domain of a function?
Ma'am, the values
Where
it
the
takes.
function is defined,
Yeah, so where the function is well defined. Okay,
well defined.
so with that concept, let's solve this problem. Which of the following are correct with respect to this function? Is this a scalar valued function or a vector valued function?
Scalar value.
Yes, because the output is a real number. It is a scalar valued function. Is it multivariable or single variable?
Multivariable.
Multivariable.
Yeah, because it depends on two variables, x and y. Scalar valued multivariable function. Okay. So here x and y are given to be real and all that. So what is the domain of this function? Okay, what is, okay, let's find out what the domain is. What is the codomain?
R.
Yeah, because it is scalar value, the codomain is R. Okay, so now let's find what is the domain of this function. At what points is this function? Okay, the domain is a subset of what?
Real number.
R2.
Greater
R
than
to the
1.
power.
R2. We know for sure because f depends on
Yes, ma'am.
x and y. We
Two
know that the
variables.
domain is a subset of R2.
R2.
Okay. So what are the points where this function is well defined?
When f of x is
Where
greater than 0,
x
ma'am.
When f
where
of x
x
is?
square plus 9 plus y
Greater
square
than or
upon
equal
16
to
is lesser
0.
than 1.
Is it necessarily f of x comma y greater than or equal to 0?
No.
No, that's not the case, right? There is a problem with the definition within this square root. Minus y squared by 60. So, do I know what square root of minus 1 is?
No.
No, ma'am, because that is an imaginary, that is
Yeah,
not there in our course, it seems.
yeah. We are dealing only with real numbers. So, I cannot have this term to be negative, right? The term within the square root.
Yeah.
So, that is my domain, right? The set of all points. Because if it is negative, then I don't know what it is. So, I want this. And what does this give me? Gives me
Option 1.
option 1, right? Yeah.
Right.
Because I just have to take these two terms to the other side. I'll get x squared by 9 plus y squared by 16 less than or equal to 1. And do you know what this structure is, mathematical structure?
That's a circle, isn't
There
it?
is
No, it's a
ellipse
circle
or
if
parabola.
these two numbers are same.
Same,
It's an
yeah.
ellipse. It's an
Ellipse.
ellipse. Yeah. And okay, in fact, this ellipse will look like the y part. It will be elongated like this. Okay, this is not a circle. Okay, something like this. Okay, so it is less than or equal to 1, so it is all the points within this ellipse. So the domain of this function is this. What about the range of this function?
Ma'am, 0 to 1. It's
Why
clear
is it
because
0 to 1?
ma'am, because we are defining the x square by 9 plus y square by 16 part to be less than 1. So
Yes. So
1
the
minus
maximum value
something
it
less
can
than
take
1.
is
Yeah.
1. Yeah. So the maximum value this function can take is,
1.
okay, x squared by 9 plus y squared by 16 is always greater than or equal to 0, right? Because both are non-negative numbers. X squared, so it's going to be greater than or equal to 0. Y squared is greater than or equal to 0. So the sum is greater than or equal to 0 and it is less than or equal to 1. So 1 minus that. Is it clear why the range is 0 to 1? And we'll take positive square root, obviously. Is it clear to everyone that
Why
the
did you
range
say
is 0?
positive square root, ma'am? Sorry, I missed that point. Why did you say we take only the positive square root?
Okay, if I take f of x is equal to square root of x, then f of, say what, 4. What is f of 4? It can be plus or minus 2, right?
Right.
Yeah, but when I talk about functions, it should take a unique value, right? It cannot take, now I won't know whether 4 goes to 2 or 4 goes to minus 2. This is not allowed, right, in functions?
Oh, yeah. Okay. Okay. That way. It's not a
Yeah,
function if it
yeah, yeah,
the output is horizontal line test or vertical line test.
yeah, exactly. So, yeah, so the range is closed interval 0, comma 1. It can take any value. So the maximum value it can take is 1. So that's going to be square root of 1 minus 1. That's going to give me 0. So 0 it can take. And 0, x squared by 9 minus y squared by 16 is equal to 0 is also possible, right? In this set of points. Because 0 is less than or equal to 1. Right? So in that case, I'll get square root of 1. So the maximum value it can take is 1. So the range of this function is 0, 1. Okay. So yes, we are considering the same function f of x comma y is equal to square root of 1 minus x squared by 9 minus y squared by 4. So this is, as already mentioned, this is an ellipse. An ellipse is written in this form. Okay. So now the question is, ellipses of increasing size represent the curves f of x comma y is equal to c, where c increases from 0 towards 1. So what do you think we should do? All the options are in the same, like it's something about increasing, decreasing and all that, but we are considering ellipses of increasing size. So what should we do in this problem? Okay, we are consider. Let's take this set. We are considering f of x comma y is equal to c. So what can I tell from here? What is f of x comma y?
It's giving a scalar, sir, ma'am.
It's given 1 minus x squared by 9 minus y squared by 4. Oh, okay, there's a different ellipse. 1 minus x squared, the square root of this is equal to c. So from this, what can I tell? From this, what
Ma'am,
can I
C
tell?
belongs
C will be
belongs
between
to
0
the
and 1.
interval 0 to 1.
Okay, that is also fine. But can I write it as x squared by 9 plus y squared by 4 is equal to 1 minus c squared? C squared 1 minus c squared, yes. Can I write it like this?
Yes.
Yeah.
Yeah, okay. So now the question is ellipses of increasing size. So by increasing size, what do you mean? The ellipse inside is smaller than the ellipse outside, right? And this is smaller than both of these, right?
Yeah.
Yeah. So increasing size just means that which ellipse is bigger. So ellipses of increasing size represent curves of this type. So f of x y is equal to c is represented like this because we have simplified, right? Yes.
Yeah.
Okay. As c varies from 0 to 1, what happens? When c is 0, what happens?
It'll be the biggest, isn't it? It'll be 1.
Yeah, exactly. When c is going to be 1, it's going to be the smallest ellipse, right?
Yeah.
Because I'll have 1 minus 1, 0. So the biggest ellipse is going to be got by putting c is equal to 0, right?
Yeah.
So as c increases from 0 to 1, the sizes of the ellipse decreases, right?
Yes, ma'am.
Yeah. So option 1 is not right, option 2 is right. And we know that it will decrease, so option 3 is also not right. It's not of constant size, right?
Yeah.
Okay. Then option 4, the curves f of x comma y is equal to c, where c belongs to 0 comma 1, cannot be represented by an ellipse. But f of x comma y is equal to c is just this, right?
It's an ellipse anyway.
Yeah, for the ellipse, we want the right hand side to be 1. So I can just divide by 1 minus c squared, right? Like I can write it as x squared by 9 into 1 minus c squared plus y squared by 4 into 1 minus c squared is equal to 1, right?
Yes, ma'am.
Am I allowed to divide by 1 minus c squared?
C being a scalar, we can do it.
No, c is not equal to 1, that's why we can do it. It's open interval 1. Closed 0, open 1. So c does not take the value 1, so I'm allowed to divide. So this is a representation of an ellipse. So the curve, this curve actually represents an ellipse. So option 4 is not wrong. It is wrong. It is an ellipse. Okay. What about f of x comma y is equal to 1? When the c is 1, what happens? What is this ellipse?
It's a point.
The
0.
origin, ma'am.
So I'll have x squared by 9 plus y squared by 4 is equal to 0. This is a non-negative term, this is a non-negative term. And if I add two non-negative terms, if I'm getting it to be 0, then it has to be, both have to be 0, right?
Yeah.
Yeah. So this f of x comma y is equal to 1 is nothing but the origin. So it's a point. So this is right. So this is just playing with multivariable functions. Okay, is this problem clear to everyone?
And just a
Yes?
question. I mean,
Yeah.
why this problem? I mean, the reason I'm asking is we have explained scalar, vector functions, and so on, multivariable functions, and then we're
Yeah.
getting into some kind of a geometric structure to understand its nature. So I'm just trying to understand the significance of this problem or the relevance of this kind of a problem.
Okay, yeah. So as you mentioned, just a geometric interpretation. But can you see that when we are moving, when we are varying this c from 0 to 1, we are looking at infinitely many curves, right? So these are actually called level curves. So this has something to do with something in week 11 that you will study. That is why. So representing a function like this where c varies, these are called level curves, and you will study something related to this in week 11.
Okay.
Yeah, so
Something
just like a
like
geometry.
a pond
Yeah.
which can hold how much water kind of thing will be the answer, sir.
Right.
Yeah.
If you take the contours.
Yeah, contours basically.
Thanks.
So say I have something. Yeah, we can take the globe, right? And it has this, what are these called? Latitudes, right? Yeah, the longitudes will be the other way. So these are latitudes. So if I slice it, then I'll find it like this, right? The latitudes are going to be like this. Or if I push the sphere to 2D, I'm going to get something like this, right?
Yeah.
Yeah. So these are level curves. Yeah. These are of the form f of x comma y, or any function f of x comma y comma z or something is equal to constant. So for each constant, it will be one curve. It's just that as the c varies, you're going to get the same curve of bigger size or smaller size. That's it.
Right.
Okay. Yes. So we know composition of functions when it is single variable, right? F composite g when it is a single variable function, how is it defined?
It's f of g of x.
F of g of x.
Yeah. So the same way we can define for multivariable functions as well. But what is the one thing that we need to keep in mind? Even when we define for one variable case, what is the domain of f?
The range
The
of g
real
of
number.
x. The
It is
range
not
of g.
necessarily, yeah. The function should be defined and on all points where g takes a value, right? So this is range of g. So the function should be defined. That is, the domain of f should contain the range of g.
Right.
Right?
Correct.
Yeah. So the same thing holds for multivariable functions as well. So composition of multivariable functions is possible only if this happens. So this is for F composite G. Here I think we'll do G composite F. Yeah. So if I have D, which is a subset of Rn, and F from D to Rm, this is a multivariable function when m is greater than, okay, this is anyway a multivariable function when n is greater than 1, right? And it will be
Yes,
scalar valued if m is equal to 1. If m is greater than 1, it's going to be vector value. Okay, so I have a function f like this, and then I have another function g, which is defined from e to rp. This p may be equal to m, may be different from n, anything is possible. So g is defined from e to rp, and it is a function e where range of f is contained in e.
means f of
So
x like this string.
yeah, this g should be well defined. Means I need to define g composite f. Okay, this is f composite g. For g composite f of x, domain of g should contain what?
Range of f.
Yeah, because it's going to be g of f of x. So at this f of x, g should be defined. So domain of g should contain range of f. Similarly, here also we'll have range of f should be contained in domain of g. And why is this E to be contained in Rm? This part is clear. Why should E be contained in Rm? What is range of f contained in?
Real number, all real numbers, whatever it might be.
No.
Rm.
F is from
In Rm.
D to Rm. Yeah. So the range of f is subset of Rm, right?
Yes,
Here. Yeah. So naturally, the domain should also be a subset of Rm, right?
yes,
Right.
ma'am.
The domain of G. Yeah. So that is why range of f should be contained in E, contained in Rm. Then if this condition is satisfied, I can define G composite f as G of f of x. Just like how we used to do earlier, just that f is a multivariable function here. That's so the composition is same as the composition that we had in single variable, but just that we'll have components. Clear? Is there any doubt about composition?
No, ma'am.
Okay. So now I have two functions, f from R2 to R and g from R to R. Can I define f composite g? Okay, tell me this. What should I have here? X or x comma y?
Only g of x will be having, ma'am, because g is a single variable function.
Yeah, so I can have only x here. So this is going to be f of g of x. Where is g of x going? Is it a real number or a scalar vector?
Scalar.
So this is going to be a number, say alpha. Can I define f of alpha?
No.
No. So f composite g is not at all defined, right?
Correct, ma'am.
Because the range of f, okay, f composite g. For f composite g, I need to take a look at range of g. Range of g, that is R, is not contained in the domain of f, R2. So I cannot talk about f composite g. Can I talk about g composite f?
Yes, ma'am.
Yes, because range of f is contained in domain of G.
Some number minus some number kind of thing, which is there in positive or negative in R,
Yeah,
and 0 is also belong to that one.
yeah. So when I have G composite F, what is it going to be? X or X comma Y?
X only.
No, what is the domain
X
of F?
comma Y. Sorry, X comma Y.
Yeah. So it's going to be G composite F of X comma Y. Okay, so let's see what the definition will be. G composite F of X comma Y is going to be G of F of X comma Y, right?
Yeah.
Yes, that's how composition is defined. Okay. So G of what is F of X comma Y?
X minus Y.
Okay, X minus Y. We know G of X is equal to sin X. So what is G of X comma Y?
Tan of x minus y.
Yeah. So G of X is sin X. So whatever variable is here, that has to come here. So X minus Y means it will become sin of X minus Y. So this is the composition, right?
Yeah.
Yes, ma'am.
Okay. Okay. What about this function? So here I have f from R2 to R, G from R to R2. Can I define f composite G? Okay, first tell me this, f composite G of X comma Y or X?
It's X, isn't it? Because G of T.
Yeah,
I'm x comma y.
because no, the domain of G is R. So
Huh.
it's going to be only X, right?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
So f of G of X. G of X, where is G of X?
So it's defined.
That is
G
an
of
X,
T,
ma'am. Yeah.
it's an R2.
Yes, and the domain of f is R2. So f composite G is defined, but in the options we are looking for G composite F. Is G composite F defined? Okay, G composite F of X or X comma Y?
X comma Y.
X comma Y.
Yeah. So G of F of X comma Y. Where does F of X comma Y go to?
R.
And the domain of G is R. So is it
R.
well defined?
Yes.
Okay. Okay, tell me this. F composite G, it is a function from what to what?
It is a function from
R2
R2 to R2.
Is it
R2
R2?
to R2.
F composite G of X is what we take, right?
R to R, ma'am.
Ah. F composite G. So the domain of this function is going to be the domain of G, and the codomain of this function is going to
Ma'am,
be the codomain of F.
F composite G, is it not defined? I mean, it is going from R2 to R2.
X into Y,
No.
sir, please.
How do you
So
define F of
F,
F composite G? It's F of G of X, right?
yes,
So you need to look at the set where the function G takes values, right? That's what you're operating first. Why did we write an
yes,
X
right.
here instead of X comma Y?
Because that's the domain of G.
Yeah, so that's going to be the domain of this function too, right? Because that is why we write an X here, F
Okay,
composite G
yes,
of
ma'am. Clear,
yeah.
right? Okay, it's taking domain and finally also it's returning R only.
Yeah.
Yeah, okay, fine, fine. Thank
So
you.
for F composite G, the domain will be the domain of the second function G here, and the codomain will be the codomain of the first function F. So what is the domain and codomain of G composite F?
It will be R2 to R2.
Yeah, the domain of F to the codomain of G. Okay, so now let's find out what this function is. So G composite F of X comma Y is going to be G of F of X comma Y. What is F of X comma Y?
E to the power of minus.
No, F of X comma Y
XY.
is here.
The value I'm talking about.
Okay, it's going to be G of X comma Y, and G of X comma Y is going to be e power x comma y comma e power minus x. This one. So this is the right option. Right?
Yes.
Let's calculate the other one. F composite g of x. What is this? F of g of x. What is g of x?
E to the power x
E to
minus
the
c,
power x comma e
comma
to the power minus x. And what is f of this?
1. So e to the power x plus, yeah.
Yeah, e to the power x into e to the power minus x. So that's 1, right?
Correct.
Yeah, so G composite F is this and F composite G is 1. So it is a function from R to R where it takes the value just 1. So it's like the unit function. All points go to 1. Okay. Yeah. So is it clear? Multivariable functions, scalar valued, vector valued and all that?
Yes, ma'am.
Yes. Any doubts? No. Okay. Okay. So when you have a one variable
And
function, yeah.
if I'm not jumping the gun, so similarly, inverse functions also would exist just like this. I'm assuming like f of x can be an inverse of g of x, therefore leading to x. Is that possible in this kind of setup?
Yes, you need to be careful with the domain, codomain and all that.
Right.
So that you get functions of this type, R to R and all that.
Okay.
Yeah.
Okay. Thanks.
Yeah. Okay. So once we had functions, we spoke about limits, continuity, differentiability and all that, right? Yes?
Yeah.
Ma'am.
Yeah. So when you had functions, the first concept that we spoke about was limits and then continuity and then differentiability. So similarly for multivariable functions too, we can talk about limits, continuity, differentiability and all that. But even before talking about limits, continuity, let's talk about partial derivatives of a function. Okay. So it'll be clear why we are jumping to differentiability even before discussing limits and continuity. So let me just talk about one variable differentiation first. So when I have f of x is equal to x squared, what is f dash of x?
2x.
2x.
2x. What we are actually doing is we are doing df by dx, right? So we are doing d by dx of x squared, right?
Yes, ma'am.
Yes? Yeah. But now we have f of x comma y. So I will say f of x comma y is equal to xy. If I want to find out f dash, if I say f dash of x, then I'm having two variables. So I won't know whether I'm differentiating with respect to x or with respect to y, right? If I just write derivative. Because I have two variables, the derivative can be with respect to any one of the variables, right?
True,
Yes,
ma'am.
ma'am.
Sometimes
Yeah.
we're taking another value also like t.
So in this case, that is when in multivariable case, you have the concept of partial derivatives. So in partial derivatives, what you're doing is you're differentiating partially with respect to x or you're differentiating partially with respect to y. So we'll see what that partial derivatives is. So now you have a multivariable function. That is when you have a question, right? If it was a single variable function, if it was depending only on one variable, then there is no question of derivative with respect to what variable, right? Only when you have that the function depends on more variables, the question arises, derivative with respect to what variable, right? Yeah. So we start with a multivariable function. It can be scalar valued or vector valued. It doesn't matter. But the only thing, the problem, the confusion arises because the function depends on multiple variables. So that has to be guaranteed for partial derivatives. So you start with a multivariable function, f of x1, x2, etc. up to xn. So this is a function, multivariable function, which depends on n variables, right?
Yes, ma'am.
Yeah. So now we talk about partial derivative. That is, we are differentiating partially with respect to one of the variables. So the partial derivative of f with respect to xi, the ith variable, that we denote by f of xi. Just like how I have written fx and fy, we denote it as f subscript xi. Or we differentiate, so we differentiate it partially. For that, we use this dou instead of d. D is derivative. This is partial derivative, a weaker case in some sense. So we use this symbol and it is defined as this limit. So what is d by dx of f? What is this limit? When I have f of x is equal to, it's a single, if it's a single variable.
When we
What is
limit
it?
h tends to 0, f of x plus h
Yeah,
minus f of x
yeah,
by h.
by h. So for partial derivatives, it's exactly the same thing that we are doing. But the only thing is that this x is not just x, right? It's x1, x2, etc. up to xn. So it's an n variable. The function is dependent on n variables. So this x is also going to be a vector with n components, right? Yes.
Yes, ma'am.
And this, I cannot add an n component vector with a number. So this h also should have n components, right?
Can you repeat that statement, ma'am, again, please?
So do you agree that this is the definition of f dash of
No,
x?
no. Just now you have said something, the same statement.
So what I'm trying to do is I'm going to try to define what partial derivatives are. So in the partial derivative case, we have a function of n variables. So if I want to define the same thing as a partial derivative, then this vector has to have n components, right?
Yes, ma'am.
And if I'm adding this vector with h, then this h cannot be a number. This should also have n components, right? Only then I can add two vectors.
Yes, ma'am. Of
All
the
right,
same
H1,
dimension.
H2 or whatever.
Yeah, yeah. So it is the same definition, just that we'll have vectors in this case. So we, instead of x, we have x tilde, and this h becomes hei. What is ei?
Is that one is a vector, ma'am? The E1 is a vector, EI is a vector also?
Unit vectors.
Yeah. What is e1 in R2? 1,
1,
0, right?
1, 0. Yes, ma'am.
So in R3, what is e1?
1, 0, 0.
Yeah, how many ever components are there in whatever space we are considering, so many components will be there, and ei will denote that the ith component is 1, all other components are 0, right?
Yes, ma'am.
Okay, understood, ma'am.
Yeah, so is hei a vector?
Yeah.
Yes, ma'am, obviously.
Yeah,
A scalar into a vector.
yeah, exactly. So I'm getting the same definition, I'm putting the same definition, just that because f is multivariable, x is replaced by x tilde, this h is still going to remain a number for me, just that to make it a vector, I'm going to multiply it with ei. So if I multiply with ei, I'm finding the partial derivative with respect to xi. So if I want to find the partial derivative with respect to x1, what should I do?
So you have to add 1, 0. So E1, HE1.
Yeah. So it will be h0, 0, 0, 0, right?
Yeah.
The first component alone will be 1. Every other component is 0. So I'll have this vector. So yes, what is derivative? What is the geometrical meaning of derivative in one variable case?
Rate of change
Yeah. So it is the rate of change
with
because there was
respect to
only one
x.
variable. Yeah. Because there was only one variable, we just wrote it as rate of change, but it was actually rate of change with respect to x. But in the multivariable case, you have x and y. So the rate of change has to be, if it's with respect to x, then you say something. If it's with respect to y, you say something, right? Because there are multiple variables. With respect to each variable, I can calculate the rate of change, right?
Yes.
So that is what is partial derivative. So when you say dou f by dou xi, it means that the rate of change of f with respect to xi. So in that case, you call it partial derivative. While calculating this limit, am I using any limit which is not known to you? H is a number, right? So it's one variable limit, right? Yes or no?
Yes, ma'am.
Yeah. So this limit is known to you. That is why we are studying partial derivatives even before studying limits and multivariable. So the rate of change with respect to one variable, just one of the variables, is called partial derivative with respect to that variable. So yeah, just like how I had mentioned earlier, we are just writing EI here, and then that's going to give me this. So the vector is being disturbed only at the ith coordinate. Every other coordinate remains the same, right?
So, ma'am, sorry, just so geometrically to understand it. So, for a single variable function, when you differentiate, you're getting the instantaneous change at a particular point. So, you get a function which will just give you the instantaneous change at that point, whichever
Yeah,
we
yeah,
are asking for. So, H is basically the small change that we're looking for,
yeah,
and
yeah,
f of x plus h minus f of x is the uh, the slope, or so the whole
yeah,
thing is a
yeah,
slope essentially, but
yeah.
with limit h tends to 0. But in a vector space or in a multivariable function, how does that visually look? So we have a vector, and what you're saying is that you are finding out with respect to just one variable, you are trying to find the rate of change. So what is that? So the output is what? It gives me a function. What is the output? I'm just trying to understand. In with respect to single variable, I kind of understand what the output of a derivative is, or what the derivative is. But in this case, what will it give me? It will give me a vector, is it, or it will?
No, it's going to still give me a function. Okay, it depends on what this f of x comma, what is the domain of this codomain of this function. If it is going, if it's say R2 to R, then I'm going to get a scalar as output. If it's R2 to R2, then I'll get a vector, right?
Right.
Yeah, it depends on the domain of the codomain of this function. But the instantaneous speed that you're looking at, in this partial derivative case, suppose you have R2 along this direction, like this is x, this is y. So when I partially differentiate with respect to x, what I get is the instantaneous speed or the rate of change along this direction. And when I partially differentiate with respect to y, then I get the change along this direction. So what is the change that is happening in this direction? When I move from this point to this point, there is change in both x coordinate and y coordinate, right?
Yeah.
So when I partially differentiate the function with respect to x, what I will know is the change in x coordinate.
Right.
Ma'am, basically it is
The
like
change along.
dropping down perpendiculars and measuring that x. It's something equal to that?
Yeah. No, something similar to that. Yeah, not equal, but something similar to that. You can think along those lines. The change in x direction is what you get by partially differentiating with respect to x, and the change in y direction is what you get by partially differentiating with respect to y. Have
So
you
in this
watched
case,
the
the
lecture
h.
video for
Sorry, go
partial
on.
derivatives?
I watched that one, ma'am, but this is more interactive, and I am able to understand much more than what
Yeah.
I
So
have heard.
I'll suggest that you go back and watch it again, because sir has given picturization and all that, right?
Yes, ma'am. The intersections he has mentioned.
Yeah. So that geometrically you can go back and watch again. And after tomorrow there's a live session, right, for the same week.
Yes, ma'am.
Yes. Yes.
Yeah. So after that, I'll suggest one video that you should watch, which is last year's revision video, in which Shubhajit has beautifully explained using GeoGebra. So that will be better if you watch it after limits, So you can watch it after tomorrow's session. I'll show you which video it is. You can watch it after tomorrow's session.
Sure, ma'am.
Okay. Yeah.
So
Ma'am,
just one final point is that h is relating to that particular xi, isn't it? Or with respect to whatever we are differentiating. That's what that h is.
H is
Even
a
though we
number.
say h, yeah, it's a number, but
Huh.
it's essentially a change with respect to that particular variable that we are differentiating.
Yeah, because we are putting HEI.
H. Right.
Every other component of this vector is going to be 0 other than the ith component.
Right.
Projecting,
which is
right, ma'am?
corresponding to this.
Ma'am, is
Yeah.
it? Yeah. Because
Yeah.
we are taking the standard ordered vector of that particular thing and then projecting it onto that, right, ma'am?
Yeah.
Can it be?
I'll not say projecting.
Okay.
Because H is a number, no? So you're
Yeah, H is a
actually
number.
doing scalar multiplication here. That's it.
Okay, ma'am.
But you can look at it this way. H is going to the vector 0, 0, 0, H 0, 0, 0. So you're converting this number into this vector by doing HEI. That's it.
Yeah, yes, ma'am.
And you're disturbing the given vector X only at this point. So only along one of the axes you're disturbing the vector. That's partial derivative. So if I want to find f dou f by dou x, so what is that going to be? It's going to be limit as h tends to 0, f of x plus h comma y minus f of x comma y by h. So when I differentiate partially with respect to x, I disturb only the x coordinate. I leave the y coordinate as it is. So can you think of this as a one variable limit?
What do you mean by that?
Yeah. So now I have f of x plus h minus f of x plus h comma y minus f of x comma y by h, limit as h tends to 0. But I can write g of h as f of x plus h comma y, right? I can define a function g as this. Can I? I'm just defining f of x plus h comma y to be g of h. So what is f of x comma y?
G of h minus g of...
No, here I have x plus h. Here I just have x. So what is the value of h?
It's minus h, isn't it? There. 0.
No. Yeah. 0, right?
All right.
Yeah. So now this limit becomes limit as h tends to 0, g of h minus g of 0 by h, right?
Yeah.
I'm just substituting. This is g of h and this is g of 0, right?
Yeah.
What is this?
Single variable.
Yeah, this is g dash,
G dash of h. G dash.
at 0, right? Yeah, so basically you're finding out g dash of 0. But it's just that because f of x comma y is f is a function of x and y, you cannot write f dash. But g is just a function of one variable, h, right? Okay, I don't think we should confuse ourselves so much here because partial derivatives is pretty simple. Okay, so this is...
May I ask a question?
Yeah, sure.
Okay, so ma'am, what we have learned is why, if we talk about X and Y axis, and when we are plotting a graph or when you're visualizing,
Hmm.
what we have learned is X is independent and Y is the dependent variable, right?
Yeah, that's when you write y is equal to f of x.
Right. So I am
Hmm.
trying to think in the same direction. So we will write, for example, Y is equal to X square,
Hmm.
right?
Yeah.
So why is this not a multivariable function?
How many variables are there in this? What
Why
is
will we
varying?
not say that there are two okay, X is
Yeah.
varying.
Yeah. Y
Okay.
is dependent on x. Y is not varying. Whatever is the variation of x, accordingly y will vary. Y is
Okay,
not
fine.
varying on its own. Yeah.
Okay. My follow-up question now, when we come to this multivariable, now X, Y, and Z,
Hmm.
right? It's in R3.
Hmm.
Uh, the function itself, now the function is X, Y, Z, X into Y into Z,
Hmm.
right?
Okay.
When we are plotting it, we are anyways taking, and we can define it X, Y, and Z. I can say X is equal to 2, Y is equal to 3, Z is equal to 4.
Hmm.
And I'm plotting it in the R3 space.
Hmm.
How that plotting is happening, because I am myself defining X, Y, Z, and then there is a function X into Y into Z.
Hmm. Hmm.
So what am I
Okay.
plotting? Am I plotting the three coordinates, or am I plotting X into Y into Z? Am I clear with the question?
Yes. So you have,
Okay.
suppose you have f of x is equal to x squared. What are you plotting here?
I am plotting Y
X comma
with
x
any
squared is the
value of
point you
X.
define, right?
Correct, right. With a corresponding value of X, I am plotting X square in
Yeah.
XY R2
Plane.
space.
Yeah. So
Yeah,
here this is x and y is dependent on x,
dependent,
and then
right,
you will plot x comma x squared, right?
right.
Okay. So when I have f of x comma y is equal to xy, what should I plot?
I will take X and Y. I will say, for example, 2 and 3 is X and Y.
And then,
And
Said.
yeah, that is my doubt. I mean, I have X and Y now. What am I plotting? Will I be plotting XY, or will I be plotting Y corresponding? I mean, I have taken Y as 3 and I take X as 2. So
hmm,
will I point on the coordinate in the R2 space to the point which corresponds to X2 and Y3, or will I correspond to 6 in the
okay.
Y space?
Um, so if I plot,
I take X as 2, Y as 3.
yeah,
Now in the
output is
R2
6.
XY space, right?
Hmm. If I plot 2 comma 3 in R2, is it going to give me any information about f?
No, it's not going to give.
Yeah. If I just plot 6 in R, is it going to give me any information?
6 corresponding to what have you taken? Or where are you
6 is a
plotting
number, no?
6?
So I'll plot it in R, right? 6 is a number
Yes.
in R.
Hmm.
If I plot 6, is it going to give me any
Yes.
information
Okay.
about f?
No, no, no.
So I'll get information about f only when I plot all three together, right?
Mhm.
So what is this? Where
Yes.
is
Okay.
this? Where is this point?
In R3.
Yeah, it's neither in the domain of f nor in the codomain of f.
Hmm.
Can you see that it is in R2 cross R?
Hmm.
Here also the same thing happened, right? R cross R. If I just give the input values, it's not going to make a difference to the, means it's not going to give me any information about the function. If I just plot the output values, it's not going to give me any information. I need to plot input
Hmm.
with output. That is when I'll get
Hmm.
information.
Hmm.
So if I take a function from R2 to R, then I will get a point 2 comma 3 comma 6 gives me full information about f, right?
Yes. So how will you plot it, ma'am?
It will be in
So
R3.
in R3. Okay.
Yeah, so the x coordinate will be 2,
So
y coordinate
fine.
will be 3, and the z coordinate will be 6 because z is
Will be the
equal to,
function
yeah,
xy. I see. Okay.
just like y is equal to x squared,
Yeah.
here it becomes z is equal to x1.
Xy. Okay. Fine.
So if I have f from R3 to R, then where will I plot?
On R.
No, what should I plot? I should plot x comma y comma z and the value, right?
Okay.
So it will be in R4, right?
Okay.
If I have R3 to R2, what should I plot? X, Y, Z, X, Y, Z, X, Y, Z plus 1, whatever is the function. I should plot everything, right? This says f of x comma y comma z is xyz comma xyz plus 1.
Okay.
So you see that this has 5 components
Mm-hmm.
because I will be plotting it in R3 cross R2, which will be in R5.
I see.
This can be seen as R cross R, right? R2 can be seen as R cross R, where the first component is a real number, second component is a real number, right?
Hmm.
So here I'm doing the same thing. What is my first component here? The first component is the point that I started with, or in this case 2 comma 3. So my first component is 2 comma 3 and the output is 6. So I will plot it in R2 cross
Is it right
R.
to say in the first case, which is R cross R?
Hmm. What is it?
No, no. So I was just saying, so is it right to say in the first case, which is R cross R, we are plotting Y in relation to X?
Hmm.
In the second case where you have R2 to R,
Hmm.
you are plotting uh, XY in relation to X and Y. So therefore it is R3. So in the second case where you have X comma Y comma XY.
Yeah. Oh, okay. In this case, R2 to.
R2 cross R,
Hmm.
right? So therefore in
Yeah.
R3 space you are plotting
Yeah.
XY in relation to changes in X and changes in Y, or rather XY in relation to X and Y.
Yeah. Here we are not talking about any changes. We are just plotting the function. We are drawing the graph of the function, right? That's what we are doing here, right? We are just drawing the
Yeah,
graph
so
of
yeah.
this. Yeah.
It's
Plotting
just
is
in
just
relation
means.
to that, right? So XY is in
Yeah.
relation to X and Y.
Yeah. So what is the graph of x as a like when you write it as set of points? It's x comma f of x, right? The graph of x. The graph of f. Yes or no?
Yes.
Ma'am.
Yeah.
So here it will just be x tilde comma f tilde. So in this case, my x tilde is this, and my f of x tilde is this. Clear? This is just with respect to plotting. We are not doing any derivatives here.
Yes, ma'am.
Yeah. Okay.
Thank you.
So if I cannot see this, I cannot plot this on a paper, right? Because when I
Yes, we
plot,
cannot.
I'll have 3 components. Yeah. So I can plot it in space. Okay. Yeah. So what were we doing? We were doing derivatives. Yeah, let's take this function to the last page. Okay. So we were talking about partial derivatives. Fx will be limit as h tends to 0, f of x plus h comma y minus f of x comma y by h, right? So in this case, there is no change in y, right?
Yes, ma'am.
So when I'm given a function f of x comma y, when I do the partial derivative with respect to x, what I should do is I should treat y as a constant. So when I treat y of a constant, when I differentiate, what will I get?
0.
Yeah. So when you're doing partial derivative with respect to x, the other variables will be treated as constants. So when I do fy, what should be treated as constant?
X.
X.
Yeah. In fact, in this case, we just have x comma y, but how many ever other variables you have, all those variables will be treated as constant. So what will fy be in this limit definition?
Ma'am, f of x comma y plus h minus f of
Yeah.
x comma y upon h.
Yeah. So you can see that x remains a constant. So that's why we can treat it as a constant and differentiate. Okay, so the example there was f of x comma y is equal to x squared plus y squared. What is fx of x comma y?
2x.
Yeah, that's because I'm treating y as a constant. What is fy of x comma y?
2y.
Yeah. So if I had x squared y squared, what is fx?
2xy squared.
Yeah. And what is fy?
2yx squared.
2x square.
Yeah. So this is easy. So these are easy cases, so there is no problem. But still, we will need this limit definition in certain places. So we will go through this limit definition and check whether f of fx is true. So this is my f of xy. So my fx of x comma y, this limit is h tends to 0. F of x plus h comma y minus f of x comma y by h. So limit as h tends to 0. F of x plus h comma y. What is this? This is my f of x comma y. What is f of x
So
plus h? Ah,
yeah, x plus h whole square
yeah. Then plus y
Plus
squared, right?
y square.
Yeah.
plus y square, right?
Minus f of x
Minus
comma
x
y.
square minus y square
Yeah. By
upon
h.
h.
So these two get cancelled. And then limit as h tends to 0, x squared plus 2xh plus h squared minus x squared by h. This gets cancelled. I can cancel this. And then as I take limit as h tends to 0, what do I get?
2x.
Yeah. So this is what we had got earlier also. By treating y is equal to constant, when you differentiate the function just with respect to x, that's what we had got earlier, right?
Yes, ma'am.
So you go by the limit or just do the way that we saw earlier. That is, treat the other variables as a constant and do normal differentiation with respect to the variable that we want. You'll get the same answer. But this limit concept is useful when you have functions of,
Ma'am, I have a small doubt here.
yeah.
Ma'am, when the question is about rate of change at a certain point,
Hmm.
is it okay to actually find the del f by del x and then substitute those points? I mean, is that a right way of doing it, or it is conceptually wrong?
You tell me. When I have f of x is equal to x squared, if I want to find out f dash of 1, what will I do?
I'll first derivate it and then substitute one.
Yeah. This is not right. Right?
Okay. Yeah, understood, ma'am. Yeah, thanks a lot.
So it's the same thing for multiple variables also. Um, okay. So yeah. Now in this case, here the function is from D to R, where D is a subset of R2, and the function is defined like this. So for points not equal to 0, the origin, the function is x squared y by x cube plus y cube, and at origin it is 0. So what will be the partial derivative with respect to x at the point 0, 0?
0.
It's not this, right? That's what I told here. Instead, what should I do? I need to find this and then evaluate it at 0, not 0, 0, right?
Yes, ma'am.
Yeah. So I need to find this first. How will I find dou f by dou x of x comma y? How will I find this?
We'll have to do f of x plus h.
Yeah, that limit thing we have to do. But what is the point that I want to find out? At 0, 0. So I can take it as 0, 0. So now what is the limit that I need to evaluate? What should I write here?
X plus h whole square into y.
No, not x. It's 0, no.
0
0.
plus h. 0
Yeah,
Zero
plus
plus
0
h.
plus
Right.
h, comma y, because I'm
Whole square,
differentiating with
comma y. Right,
not
right,
y,
right.
0.
Yes, ma'am. Again 0.
Yeah, minus f of 0, 0 by h. What is f of 0, 0?
0.
0.
Yeah, this is 0. It's given. And this is f of h,
H
comma
comma 0.
0. My h is not 0, right? It's use this or this.
The first one.
Yeah, because h is not equal to 0. And when h is not equal to 0, I will fall into this category. So I'll have limit as h tends to 0, f of h comma 0. So wherever I have a y, I'll put 0. So the value is, yeah, 0 by h. So it's 0, right?
Yes, ma'am.
This is not because of this. This 0 is not because of this. I think even for derivative with respect to y, we'll get 0 because I'll have 0 comma h. So even with the other case, you'll get 0. So dou
But
f
just like
by
single variable functions, you still have to look for whether the functions are continuous and all that, right? Before we can differentiate.
no, we are doing partial derivative, right? I did not even talk about continuity of multivariable functions. Even before that, we are looking at partial derivatives, right?
Right. No, for
But
normal for single
why is that,
variable.
ma'am? I mean, why it needn't be continuous? Because rate of change has to be continuous, right, ma'am?
No, it's not that. In the case of one variable, do you mean?
Yeah, here, ma'am. Why aren't we looking at the continuity before we do the differentiation like we did in the one variable case?
So for differentiation, the differentiation in one variable case is actually the differentiation in one variable is this concept gets generalized to differentiation in multivariables also. So there's something called total derivative. So when you're talking about total derivative, that is when you will talk about the continuity and all that. But with respect to partial derivative, are you actually looking at the function as such? You're just treating at the changes along one direction, right? The function is something like this. But you're not worried about what is happening to the entire function. You're just seeing what happens to its changes along one direction.
Yeah, yes, ma'am. It's
So
like
you're
the
actually
sine
not
curve. It's like the sine curve which Sir showed in one of the videos, right, ma'am?
what was
I
discussed
mean,
about the
he
sine?
showed the sine xy curve and then he intersected it with the x-axis and the y-axis.
Yeah. So you have the curve in 3D, means
Yeah,
you have the surface in 3D, and then you're just talking about what happens when you intersect it with the plane.
yeah, yes, ma'am.
If that
Okay.
plane is parallel to x-axis, you're talking about the derivative with respect to x and all that.
Yeah. So, but wherever it is not continuous, there will be a gap, right, ma'am? In
Yeah,
such a
so we
case,
still haven't discussed continuity, right? We
yeah,
don't know
yes.
how to find limit in multivariable case. Yeah.
Okay, okay, ma'am.
But
So
I think
that you
the question is is continuity not a precondition to differentiation
no,
itself?
no.
Okay. But in single
To
variable
partial
case, it is, isn't
differentiation.
it?
For partial differentiation, it isn't. But there is derivatives in multivariable case. That's what I said is total derivative.
Even in partial derivatives, even in that single direction that you're trying to differentiate, it has to be continuous within that direction, right?
No.
I don't know if there's such a concept exists, but what I mean is, so suppose you're differentiating with respect to just x and treating y as constant, then it has to be
What do you
continuous
mean by
within x.
continuity along x? It doesn't make sense, right? Because the function is dependent on both x and y. You cannot talk about continuity along x or continuity along y. What we are doing in partial derivative is we are seeing the rate of change along one direction.
All right.
How the function is changing in this direction, how the function is changing in another direction.
So suppose I have a graph or whatever, the graph
Surface.
that looks like, a plane which is kind of flowing from one point to another point, and then there is a break and it flows from another, break and then it flows. Will I be able to do partial differentiation at all in the point where it breaks?
Yes.
Okay.
In fact, when you calculate, let me just check what will be the limit of this function. Yeah, the limit of this function does not even exist at 0. So if the limit doesn't exist at 0, it's not continuous, right?
Right.
In tomorrow's session, you will see that the limit of this function doesn't exist.
Right.
And if the limit doesn't exist, it cannot be continuous. But still, we are talking about partial derivative.
Partial. Okay, man, I think I'll wait for some more understanding before I'm just trying to understand the visual aspect of it, but it's okay. I think I can wait.
Yeah, so that's why I said that after tomorrow's session, you should watch last year's session, which I mentioned about the GeoGebra thing that he used to explain. That was actually a revision session. So that contained all concepts of week 10. So everything put together, it was so nice visually. I'll show you what video that is. You can watch that after tomorrow's session so that you'll enjoy it better.
Sure, ma'am. Thanks.
Okay. So similarly, you can calculate the partial derivative with respect to y at the point 0, 0, right? I'll do the same thing instead. F of 0 comma h minus f of 0 comma 0 by h, right? It's again going to be 0, but still, yeah. Okay. Then, yeah, this function f of x comma y is xy by x squared plus y squared. Identify the correct options. Okay. So what is limit is, okay, what is okay, how will I find the partial? What is dou f by dou x? I'll treat y as a constant and differentiate with respect to x, right? Yes?
Yeah, correct, ma'am. 0
So
minus
how
2x
do I
x.
differentiate?
Same
What
as
should
we
I?
did in the last question. We can take 0 plus h and then
No. I'm
0, 0.
talking about in general. Dou f by dou x at x comma y. So I'm talking about general derivative.
It
I'm
is
not
at
talking
f. It is at f dash g minus g
yeah,
dash f and
quotient rule.
by quotient rule. Yeah.
Yeah. So you just have to square the denominator and then write the denominator as it is and then differentiate the numerator. What is the derivative of x comma y, x into y? Partial derivative. I'm doing partial derivative. So what will I get here?
Just y.
Yeah.
Y.
Minus, keep the numerator as it is, differentiate the denominator. What will I get?
2x.
Yeah. So this is dou f by dou x. X squared plus y whole squared. Numerator is x squared y minus 2x squared y. So that's going to be y squared minus x squared. So this is dou f by dou x. Can I say dou f by, this is dou f by dou x? It's a function of x and y. dou f by dou x at 0, 0. Can I just substitute 0, 0 and find the value?
Undefined.
Yes.
Yeah, you'll get 0 by 0. No, you cannot do that because you'll get 0 by 0. So what should I do? I know this formula, right? Limit as h tends to
Differentiate
0.
again.
No, 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 you cannot do that here. You're talking about L'Hopital's rule, right?
Yes, ma'am.
But what will you differentiate it with respect to? Again, that question arises, right?
Yeah.
So you just use the limit definition. If things don't work, go back to the definition. That's so limit as h tends to 0. What is this?
Had
F
it
of
not been, ma'am, had it
ah,
not been 0 by 0, could we have substituted it? No,
yeah.
right?
Take option 2. Dou f by dou x at 1, 1. What is at 1, What is the value at 1, 1?
It is again 0. But it's not 0
It's
by
0.
0. Yeah, it's not
Yeah,
0 by 0.
yeah.
Yeah.
And what about this one? 1, 0. Oh, again it's 0. Okay, let's find dou f by dou y. Then we see dou f by dou y at x, y. What is this? Again, I'll do quotient rule, right? Because there is a y in the numerator as well as denominator, right?
Yes, ma'am.
Denominator will be x square plus y the whole square.
Yeah. And then keep the denominator as it is, differentiate the numerator. But I'll be differentiating with respect to y. So I'll get x minus, keep the numerator as it is, differentiate the denominator with respect to y. So x is treated as a constant, I'll get 1, right? Yes?
Yes.
Yes or no? Does everyone agree with this? These two?
Yes, ma'am.
In this case, df by
Numerator
d
will be x
dou
cubed, Amma.
Will it be x cube? Oh, yeah. Sorry. Yes. There was someone asking, no? D f
so
by.
here dou f by dou y 1, 0 will be 1.
Yeah.
So
Because
you
it's
can
not
directly
going to give me
substitute.
0 by 0 form. Yeah, so I can substitute.
Yeah.
So I'll get 1, 0, I'll get 1. So this option is right. What is dou f by dou y at 1, 1? 1, 1 is going to be 1 by 1 plus 1, 2 squared, 1 by 4, right?
Yes, ma'am. 1/4.
Yeah, so this is not right, this is right. But 0 at 0, 0, I cannot use this substitution because I'll get 0 by 0 form.
So
So
it's
for
simply
that,
just not defined. That's it, isn't it? We don't have to go back to x plus h, f of x plus h
no,
method.
if I have 1 by 0, then it is fine. But I'm getting 0 by 0, no. So what is 0 by 0? It's indeterminate. So I need to go back to the definition. At 0, 0 is going to be limit as h tends to 0, f of h, 0 by minus f of 0, 0 by h, right? Okay, f of 0, 0 is not defined because I'll have 0 by 0 form. The function should have been xy by x squared plus y and 0. Okay, so now what is f of 0, 0? F of 0, 0 is 0, right?
Yes, ma'am.
Yeah. So I'll have
F
limit
of
as
h
h.
comma 0 upon h.
Yeah. F of h, 0 is 0. Okay. It's 0 by h. How did I get 0?
0, comma 0 is still undefined, isn't it? Oh, sorry.
No, I split the function. Because when I put 0, comma 0, I'll get 0 by 0 form.
Yeah.
Ma'am, it would be 0. F of
Yeah,
h
in
comma
this case
0.
it would be 0. Okay, then why is dou f by dou x not defined at 0, comma 0? Yeah, I think because the split of this function is not given.
Ma'am, out of law, I'm asking, ma'am, when we'll be doing dou square f by dou x square kind of things, we'll be using those ones?
Uh,
Double partial derivation kind of thing.
yeah, so when you want to find this dou f by dou x is again a function of two variables, right? Here.
Yes,
So now
ma'am.
when I want to find the derivative of this, again that becomes a question, right? Question derivative with respect to what? So that's when you will have dou f by dou x derivative with respect to x. That's going to give me dou squared f by dou x squared. Dou f by dou x with respect to y is going to give me dou squared f by dou x dou y.
Okay, we'll not be using these kind of things in our course, no, ma'am. Hello.
Yes or no?
We
And we
lost your
lost you
voice, ma'am.
briefly.
Oh, is it? Till where did you hear me?
Dou square f by dou y dou x.
Yeah. So I just asked, is this what you asked? Like, were you talking about these derivatives? Yeah, this is second order partial derivative with respect to x. This is second order partial derivative, mixed second order partial derivative. Because it contains both x and y.
I'm asking whether these kind of things will be using in our course or not, ma'am. That's all.
Yes, we will be using. We will be using to find critical points and all that.
Right, ma'am.
But it
Thank you.
will be for functions of simple type where you needn't use limit and all that.
Okay, thank you, ma'am.
Yeah. Okay, so I need to check why this is not defined. Dou f by dou x at 0, comma 0. Um, okay, shall I post it on discourse? I don't know why I'm getting 0 as the answer.
Yes, ma'am, sure.
Yes, ma'am.
Yeah, let me
But
just check
ma'am,
this.
in general,
Yeah.
if we find this dou f by dou x, and if we get
Hmm.
an undeterminate form, then can
Hmm.
we say it is not defined, or we would have to check using the limit theorem?
Yeah, you need to use the limit because indeterminate form is not same as not defined. Like 1 by 0 is not defined, but 0 by 0 is not defined. This is indeterminate form.
So that, ma'am.
Yeah, it's again going to be 0, right? Um, okay, let me check this and I'll post it on discourse. Or probably this definition is not right. F of x comma y is 0 when 0 is. Okay, let me check that.
Ma'am, is there a scope to connect with the you or any of the course instructors apart from the scheduled time? Uh, if there are some
Always on
questions which,
discourse.
yeah, ma'am, what my objective was, there are some things which we cannot just put on discourse. For example, in week 11, right?
Hmm.
The lectures when we are seeing, the hand movements of the professor in terms of making it visual, it's just not getting through. So we would, at least I would like to connect with some of the course instructors to understand what the professor is saying and what he actually means. Is the understanding right? So I cannot put this on the discourse, and I would not be able to read the explanation also through the discourse. And that is where I was coming from. That's an individual objective. When you take these sessions, we have to definitely follow the guidelines and be a part of the common objective that you are trying to achieve with all the students. So is there scope or possibility where we can seek time from you guys as convenient to you, and maybe an hour or so session where we can specifically ask what are the doubts that are coming from the lectures and make our concepts more stronger over and beyond what you guys are taking these sessions?
Yeah,
So
you can
one of the
ask us
questions,
any
for
doubts
example,
even during the live sessions, right?
no, that's what I'm saying. For example, it's a common objective that other students would be interested to hear what is the revision happening, right?
Mm.
That might not be of interest to all the students.
Yeah, so we can
Say
have it
the,
at the
for
end of the
example,
session.
the question that I took XY thing, how it is getting visualized, right? It
Mhm.
was not necessarily a part of this particular revision session. It was over and above. So is it fine? I am more than happy to stay beyond those particular time that you have taken the live session, but will it be okay for you also to stay
Yes,
beyond
yes,
those particular time limit and
definitely.
thing? Okay,
Yeah,
fine. Then it's
yeah.
okay. Sure, ma'am.
So we
Thank you.
don't fix
Then
this
it's okay.
live session from like 5 to 6, right? We just go on till it ends. So
Fine.
till whatever we do.
Then
Yeah,
it works. Sure, ma'am.
yeah.
Thank you. Fine.
Okay, so I'll.
Especially when sir is explaining about multi-curves kind of thing, with his hand movements, we are not able to visualize correctly or clearly now. Our imagination, whether it is correct or not, we don't know. That is the problem.
And week 11
Okay,
is really, I mean, the movements is, he takes his hand somewhere, and what does he mean with all those particular things? You might be ending up interpreting wrong. And hence, I want
okay.
to just be on the same page in terms of what we have interpreted.
Yeah. So you can actually ask it during that week's session. Like this is week 10 session, right?
Yes, sure,
So
sure,
yeah,
sure.
because we make sure
And
we
that is
watch
what
the
was
video
in my
before
mind.
we, yeah,
Yeah,
because
that is
we
what
watch
was
the
in my mind
videos
in
and
terms of week 11. If we can spare some time to understand what exactly that interpretation is, because visual representation is very much required from these lectures perspective.
yeah, I understand.
It works,
Okay,
ma'am. Even after the live sessions, I can stay and ask those particular things.
yeah, okay.
Thanks.
So these two, let me just confirm if this is right. Okay, then yeah, then what we have what is called as directional derivative. So when we do partial derivative, what we are doing is we are doing this change of the function along x direction is dou f by dou x, and change along y direction is dou f by dou y, right? But these are not the only directions, right? In R2, for example, this is a direction, this is a direction, this is a direction, this is a direction. Yes?
Yes,
So,
ma'am.
yeah. So that is when the picture, this comes into the picture. The directional derivative comes into the picture. So here, what did we do? We just did h into ei, right? Where ei represented whatever direction we were looking at. If it was x, it would represent x direction. So it would be 1, comma 0. If it was y, it represented 0, comma 1. That is the direction, y direction. So the same thing we will do for the other directions too. We will take the unit vector along those directions. So do you agree that all these are unit vectors? 1, comma 1, 0, 0, 1 and all that?
Yes, ma'am.
These are unit vectors because the norm is 1, right?
One.
When we
Yes,
talk
ma'am.
about norm in general, we usually take the dot product norm. So the norm of these vectors is 1. So these are unit vectors. So along any other direction other than the standard directions, when we take the derivative, that is called the directional derivative. So the rate of change of the function in the direction of u. So direction, when we take a direction, we take a unit vector. So when we do that, that is called directional derivative. and we represent it using duf, where this u is the direction and we differentiate the function f. So it's the same. The definition is exactly the same, just that instead of HEI, I'll have HU, where U is this unit vector. So is it clear here? We have x1 plus u1h, x2 plus u2h, etc. xn plus u1h. This gets replaced with HU. Is it clear? This is a unit vector. So what are we doing in partial derivatives with respect to x and y? We are checking the rate of change along x direction, along y direction, right?
Yes, ma'am.
When with respect to directional derivatives, you check the rate of change along a direction, which is other than the standard directions. That's so it's the same limit definition instead of HEI, because 1, 0 represents x-axis and change along x-axis will be obtained by doing HEI. Change along y-axis will be obtained by putting 0, 1, like H01. So change along any other direction will be obtained by putting U, that direction, instead of EI. Is it clear?
Ma'am, can you explain it through a graph? And what exactly would it mean through a unit vector in the direction of a unit vector?
Okay. So you've
Is it
watched the
possible?
lecture videos, right?
Yes, I
Okay.
have seen.
So do you remember sine xy, the graph of sine xy?
Yes, I remember.
Okay, I am not very good in GeoGebra because I don't know most of the commands, but let me
And
just
this is
try.
what I meant. For example, GeoGebra, we really don't know how to use it. So these offline sessions would be very helpful if we can clear our concepts from that perspective.
Uh, okay, I just watch YouTube videos and do things. Okay, I don't even remember what I should select. Was it this?
I mean, it's GeoGebra
Start calculator.
3D
Ma'am,
or
start
yeah,
calculator.
stat calculator.
Okay, I should do this.
It's on the top.
Oh, this one, somewhere here it is.
Ma'am, and graphing, you can choose, no, ma'am,
Oh,
on the graphing, 3D. And in the input, you can write sine xy.
the tutorial videos I made, I just learned how to do those things and then I never used this. Okay. So this is sine xy, and then what do I do? How do I add? I add an expression. Okay. How do I find derivative? Partial derivative with respect to x. So that's going to be derivative f with respect to x. Okay. So the derivative with respect to x, dou f by dou x is going to be cos xy into y. That is right. Right?
Correct.
Yeah. So this is the graph of the function. So this is my sine xy from top angle. Yeah, in some sense for a top angle. So when I talk about the derivative, a partial derivative with respect to x, this is what my partial derivative with respect to x denotes. So how am I getting this function? Do you see these lines?
Mm-hmm. Yes,
Yeah.
the gray
So
lines,
what?
right?
Yeah.
Yeah.
The black or gray or whatever. Yeah.
Yes,
So
yes. Hmm.
what you actually do is you take this function and then you slice it along. So say if my green is y, red is x. Okay, something. Okay, either of them. I don't know. I think the red is x-axis and green is y-axis. So what I do with respect to x is, if I want to calculate the partial derivative of f at the point say 1 comma 0, what I will do is I will slice this portion of this surface. So this is a 3D figure. So what I will do
Hmm.
is I will slice it along this this plane x at 1 comma 0. So if I want at 1 comma 0, what I will do is, okay, in fact at 1 comma y, say if I say 1 comma y, I will slice this curve along this line. X is equal to 1 and y varies. So I will slice it. So in that case, I will get a 2D thing, right? I don't know how to do the slicing here. I should
Yes, ma'am.
intersect it.
It'll be a 2D, and then you'll find those lines there wherever it
Yeah.
is intersecting.
And then you will find the derivative uh, in the next step. So that's what you will basically do. How do I write it? So I want, say, x is equal to 1. Yeah, I get this plane. Right, perfect. So I will get this plane. So now how do I get the portion just on the plane?
Just
How
tick
do
mark
I?
that f of xy, and we'll be getting that point or line kind of thing.
No, I have to intersect f
Untick, untick.
with. Yeah, I got it. Okay. So yeah. So now I get this curve, right? This is I have
Okay.
now, yeah. And now I get this function. So what is this function? It's going to be this sine of x comma, okay. It's going to be intersection of these two curves. And I find the derivative of this. Now this is a single, you will treat it as a single variable function. Okay, I think for this I will do with respect to y because I haven't varied x. I have fixed x and I have varied y. So I'll find the derivative with respect to y. Now this is partial derivative for me. When I take the derivative after this. Like
I see.
when I
Okay.
differentiate this, yeah, with respect to y. Because x is equal to 1 throughout for this.
So the red that you were showing, it would fall, it would be some on this line somewhere, right? The graph that has come.
Yeah. When x is equal to 1, it will be this.
When
No,
x,
this
okay.
is the function. I need to differentiate that function. So I will get the cos curve. So how do I differentiate equation 2? Equation 2 has x is equal to 1, so y is a variable. So derivative of equation 2 with respect to y.
Why?
What did I do? Derivative capital D, is it?
Ma'am, it should be A, I think, instead of equation 2.
No, if a is already the derivative. It's already the derivative of f. Partial
Okay.
derivative.
Okay, so
Yeah.
you're trying to intersect the, do the derivative for the intersect part.
Yeah,
Path.
yeah, yeah.
Okay, okay, ma'am.
Um, Maybe I need to do something here to consider it as a function. That is why I think I'm not getting the
Yes,
derivative.
maybe. Maybe
Yeah,
it's because of the syntax then.
yeah. So you should watch Shubhajit's video. He has done it beautifully. He has done
Okay,
partial
fine.
derivative and he has done limits, directional derivative, everything.
After tomorrow then.
Yeah, you should watch
Okay. Yeah.
continuity and all that and then watch that.
But many thanks for this explanation also. What we were able
Yeah,
to
no
visualize,
problem.
many thanks for it.
Yeah. This is what Sir has done in the video also, right? Like he takes the surface, slices it, and then that's what I remember.
मैं बट समझ में नहीं आता वीडियो देखकर सिर्फ.
Yeah, I think you should uh, what come here and then understand from here and
Yes,
then go
sure.
and watch that again.
Exactly.
Yeah, because
Exactly.
Sir
So
is also very
additional
good with
resource
this.
definitely is needed. And when you again watch the lectures, then it makes a lot of sense. Lot of things get
Yeah,
clear after hearing you or some additional resource. That's for sure.
yeah. Okay. Yeah. So the concept of directional derivative is also the same. Like instead of along the x-axis and y-axis, it's along some other direction that we are looking at. So we do the same thing. Just that instead of HEI, we'll have HU where U is the unit vector along that direction. And in fact, there's a much simpler way of calculating directional derivative once you know what the gradient of a function is. So yes, you can always use that to calculate instead of using the limits, but still for the sake of simplicity, we will, means to understand what the definition is, we will do a few problems. Okay, so I have the function f from R2 to R, I have f of xy is equal to x plus y. I need to find the directional derivative in the direction 1 comma 1, in the direction of the vector 1 comma 1, along this direction. So what is the unit vector in that direction? How will I find the unit vector?
By dividing by
Dividing
its
by the
norm.
norm.
Yeah. So what is the unit vector that I will have?
1 by root 2.
Root 2.
Yeah, 1 by root 2, 1 by root 2. So I need to find the directional derivative along this direction. Means this is my unit vector. So du of f, or in fact dv along that vector. Any vector I will normalize and then do. This is going to be limit as h tends to 0, f of x plus hu minus, okay, comma y. Sorry. It won't be x plus hu, right? It will be x tilde. That is x comma y plus hu minus f of x comma y by h. Right?
Yes, ma'am.
Agree? Yeah. So this is going to be limit as h tends to 0, f of x plus h by root 2, comma y plus h by root 2 minus f of x comma y by h. So can you see that you just cannot differentiate taking one as constant, one variable as constant and all that here? Because both are varying, right? Only along the x-axis and y-axis, one of the variables will vary. Along any other direction, both the variables will vary, right? Yes?
Yeah.
Yeah. Okay. So what is this? F of x plus h by root 2, y plus h by root 2?
X plus h by root 2 plus y by y
Yeah.
plus h
And then
by
when I subtract x and y, I'll get h by root 2 twice, right? And then I have a 1 by h. That is everything divided by h. So this is square root of 2,
root 2.
right?
Yeah.
Yeah.
So
So the following
what
of,
is this
yeah,
root 2? Root 2, how will we say? The
the rate
function
of
changes.
change,
Yeah.
yeah, the rate of change of this function along this direction is root 2. It's a constant rate of
Constant.
change.
Per
That's why it doesn't
unit
change.
change of the unit vector, per unit, right? Per unit movement of u, the function is changing root 2.
Along this direction, the function is changing. The rate of change of this function is root 2 along this direction.
Okay. And rate of change obviously will mean per unit movement.
Uh, Rate of change.
Yes, ma'am. According to
Rate of
physics,
change, rate of
Yeah,
change in
yeah, yeah,
respect to what?
yeah,
So
yeah.
rate of change in respect to x and y per unit, this is how the function is changing, is the interpretation of root 2, right?
Yes, yes, yes. For
Ma'am,
every, yeah,
ma'am, with respect to x and y or 1 comma 1?
along this direction. So x and y will be moving here. X will be equal to y along this direction. So along this direction, x will be equal to y, right? So it will be like 1 comma 1 to 2 comma 2 to 3 comma 3, right? The rate of change of the function along this direction, and in this direction x is going to be equal to y, right? Along this direction.
Yes, ma'am.
Yeah. So if I want to find the directional derivative of f at a point say 1 comma 0, instead of x comma y, I'll just put 1 comma 0. Here again I'll have 1 comma 0. In this case, for any x comma y, I get the derivative as, means the directional derivative as root 2. But at a point, if I calculate at a point, see this one, f of x comma y, x1, x2, xn. If I substitute particular values for this x1, x2, xn, then it's going to be the same. The limit definition is going to be the same. I'll get the same value anyway. In this case. So the answer is root 2. Let's try another problem. Yeah, this one is interesting. So once you know the gradient of a function, this problem is going to be very simple. But using the limit, just for the sake of completion, let's solve this problem. So I want to find the directional derivative of this function at the point this in the direction of this vector. So is this vector a unit vector?
No.
So what is the unit vector? That is, what is the unit vector along this direction?
Root 5.
Ma'am, divided
Divided by
by
root
2,
5.
No,
root 9.
divided by 4 plus 4 plus 1. That's root 9. So that's going to be 3. So the unit vector is going to be 2 by 3 minus 2 by 3, 1. So I want to find dvf at the point 1, 0, 1. So what will the thing be? Limit definition be? Limit as h tends to 0, f of
F of 101, which would be 1 into
no,
e raised to power
f of this plus h times this, right? This, right? And then f of 101. Agreed?
yes.
Yes, ma'am.
Yeah. So this is limit as h tends to 0, f of 1 plus 2h by 3, comma, minus 2h by 3, comma, 1 plus h minus f of 101 by h, right? What is this? F of x is xyz is this. So what is this?
1 plus 2h by 3 e raised to power minus 2h by 3.
1 plus 2h by 3 into e power minus 2h by 3. Yes.
Minus
Plus
2h by 3,
minus 2h by 3 e raised to 1
1
plus
plus
h.
h. plus 1 plus h.
e raised to 1 plus 2h by 3. You can also do x comma y comma z and then finally substitute x, y, z, but I have directly used 1, 0. Minus f of 1, 0, 1. That's going to be 1.
A.
Oh, that's going to be 1. Y is 0. Z is 1. E. Right? It will be a minus here also. Right?
Yes. E
By
raised to
h.
power x, right?
Okay. So now let's simplify. Limit as h tends to 0. Okay. I have e raised to minus 2h by 3 by h plus 2 by 3 e power minus 2h by 3 minus 2 by 3 e power 1 plus h plus e raised to 1 plus 2h by 3 by h plus e raised to 1 plus 2h by 3 minus 1 by. Okay, there's something wrong. Something should get cancelled here. E raised to.
Ma'am, sorry to go back
Yeah.
kind of thing. Why last?
Oh, what is it?
Yeah, in the unit vector actually, 2 by 3 minus 2 by 3, and the last one,
Oh,
something
sorry.
1 by 3, I think.
Yeah, yeah. So that's going to be h by 3. So where will I get h by 3? Here I'll have h by 3. Here I'll have h by 3. So that would be h by 3 here. And then here I'll have. Right? Yes, I guess. I think I have missed out something. Okay, let's try. Is this clear? I'm just splitting it into two terms. E power 1 into e power h by 3.
Yes, ma'am.
Yeah. And then I'll have e by h plus e power 2h by 3 by h plus e by 3 plus e power 2h by 3 by 3 minus 1 by h minus e by h. This 1 by h has to cancel with something. I'm missing something. 1, 0, 1. So that would be 1 into e power 0 plus 0 into e power 1 plus 1 into e power. So that's going to be 1 plus. Okay, let's check. This gets cancelled. This has to cancel something. Plus 2h by 3 into e power y minus y Z this power by h plus 2 by 2 minus 2 plus by h plus again I'm missing out on something. Okay, for now let's assume this is not there. But if I take limit as h tends to 0, what will this value be?
2 by 3.
Yep, this is going to be 2 by 3, and this is already minus 2 by 3 e. This is minus 2 by 3, because as h goes to 0, this goes to 1. Yeah, let's keep this, plus this becomes e by 3, and this becomes 1 by 3, right? This and this is left out, right? This is
Yes, ma'am.
this and this. So this has to cancel out with something, because when I solved it, it cancelled with something. And there's a post on Discourse on this problem also. So even there it got cancelled. I don't know what I'm missing here. Okay, so let's forget this for now. So this simplifies to 2 by 3, 2 by 3 gets cancelled, minus 2 by 3, e by 3. So that's going to be minus e by 3 plus 1 by 3. Okay. What about this term? What is limit as h tends to 0 of this?
One.
It will be 1 by 0, right? No?
Yeah. Oh, 1 by 0, 0. Yes. This is what I'm doing wrong here.
Ma'am, this e to the power minus 2h by 3 plus e to the power plus 2h by 3 upon h would collectively make 1 by h and would finally cancel minus 1 by h.
Oh, where? Which one?
Ma'am, the two things that we have encircled, e to
Yeah.
the power minus 2h by 3 upon h and e to the power 2h by 3 upon h. These two would get us 1 by h and would
How
then
do we get
finally
1 by h?
mm,
That is the addition.
Only if you multiply, yeah, this is addition.
Yeah, this is addition. What am I doing wrong? Okay, I think we go with x and see what happens. I just answered a post yesterday on Discourse on the same problem, and I got the right answer. Okay, so limit as h tends to 0, f of x plus 2 by 3, y minus 2 by 3, and z plus 1 by 3 minus f of
2h by 3, isn't it?
yeah. Okay. Well, let me open that post, because I don't think I'll do it right. Um, do you remember which activity question this is? This is 10.3, right?
Yes, ma'am.
Was it question 3? Yeah. What was it here?
It's question number 3, ma'am.
Yeah. Can you see the calculation?
Yes, ma'am.
How did it get cancelled? What did we do wrong? Yeah, the terms here will get cancelled with the terms here. So this is exactly what we did. Okay, so there was a mistake in his calculation, which I said, yeah, these two terms get cancelled, and then the term that is left. Okay, maybe we'll just do it again. I'll keep a 1 by each outside plus y e power z plus z e power minus 1 into e power 0, 0 into e power 1, 1 into e power 1, e power minus h by 2 plus why am I not getting a minus 1? Can you identify my mistake? Okay, if I do it as x, y, z, what will I get? Yeah, in this case, terms are getting cancelled, right? Are you there or am I audible?
Yes,
Yes,
ma'am.
ma'am, you're
Yes, ma'am.
audible.
You are
We
audible.
are we are with you, ma'am. Actually, we are also trying along with you where we
Okay.
went wrong, kind of thing.
Yeah, in this case, terms are getting cancelled, right? Like, can you see when I write it as x, y, z, terms are getting cancelled. So I think when we substituted the values, there is something that we are going wrong.
But that shouldn't be
Because,
the case, right, ma'am? I mean, it should work both ways.
yeah. X e power y, there's one here, and then y e power z is there. X e power z, everything is there. And then I will be left out with 1 by h times x e power minus 2h by 3 plus 2h by 3 into e power y minus 2h by 3 plus y e power h by 3 minus 2h by 3 plus e power plus now as h tends to 0, as h tends to 0, I get Okay, so shall I post this also on Discourse? I'll solve this and post it.
Please, ma'am.
I have,
Meanwhile, we'll be also trying to calculate that one.
yeah, at the point 101, this should be 101. Yeah, so what is the answer with this? Yeah, 1 by 3. Okay, so I am still not able to figure out what is wrong. And I'm not even able to relate to the comment that I wrote on Discourse yesterday.
Nothing but some expansion. Because of space, actually, you have tried to make it as calculated as possible. If we coolly
No,
do
but
that
the
one,
limit of this as h goes to 0 is clearly the numerator goes to, as h goes to 0, what do I get for the numerator? I get 1, right? E power 0, 1. So I
correct.
get 1 by 0, right?
It's goes to zero. Okay. Yes, ma'am. So that should be cancelled somewhere, I think.
One last shot. Do you mind just walking us through step by step so that it might be just easier? I think we also got lost in a myriad of
Yeah.
numbers.
Nothing but some space problems, sir, that's all. If we do it on ourselves coolly tonight, and even though ma'am is giving that answer in the discourse, we can just
Yeah, I think
recalculate and check that
because
one.
if we keep doing the same thing again and again, we will not probably identify our mistake. We should give a gap and then try to write it down. Okay, let me just check if the answer is right. Yeah, definitely it has to be right. Power y. I'm just calculating gradient. E power y plus z e power x e power z x power at the point 1 0 1 plus e 1 plus e 2 by 3 minus 2 by 3 and 1. 1 by 3. So the answer is e by 3. 6 times e by 3 is 2e. Right. The answer is right. I don't know what I'm doing wrong in the limit. Yeah, I guess we should give it some time and work it out. We probably find the error. Okay, so I will do this one and that not defined thing. This,
All right, ma'am.
yeah. Okay. So anything else with respect to directional derivative, partial derivative? I've included one more problem. So yeah, how will we find the directional derivative here? So directional derivative of this function at the point this in the direction of the line PQ, where PQ is given, Q is given. So how will we find the direction here? P is 1 comma 2, Q is 4 comma 6. This is PQ. How will we find the direction PQ? It's just difference between the coordinates, the difference vector. 3 comma 6 minus 2 is 4. It's this vector. This is the direction.
Ma'am,
Means
how the difference is direction?
yeah, so it's something like this vector to this vector, and this is PQ. So that resultant vector, no? V1, V2, this is V1 minus V2. This is P, this is Q. So what is this direction? It's the difference, right? The resultant vector.
Yes, ma'am. Yes, ma'am.
Yeah. So I want this. I know V1 and V2. I want V1 minus V2. So it's like 1 comma 2 say it's here, 4 comma 6, 4 comma 6 say it's here. So it's this vector and this vector. I want the line joining P and Q. For that it will be something. I may be wrong with the arrows. So this would be V1 minus this is V1, this is V2. So the direction is along 3 comma 4 and when I want to convert it to unit vector, I'll get 5, right? 1 by 5, 3 comma 4. Maybe we'll try to solve this problem. The directional derivative along V of this limit as h tends to 0 of f of x plus 3 by 5h comma y plus 4 by 5h minus f of x comma y at the point 1 comma 2, so we can do that 1 comma 2 by h. So this is 1 plus 3 by 5h squared plus 2 plus 4 by 5h squared minus 1 squared minus 2 squared by h as h tends to 0. So this is 1 squared gets cancelled. I'll get 6 by 5 h plus 9 by 25 h squared plus 4 gets cancelled. 8 by 5 h plus 16 by 25 h squared by h as h tends to 0. I'll get 6 by 5 plus 8 by 5. Right?
Correct, ma'am.
Is 14 by 5 4.4? No, it is not. Did I get 14 by 5? 3 2 are 6. As h goes to 0, this goes off,
That'll
this
be
goes off.
16 by 5 h, isn't it? That'll be 2, 8, 16 by 5 h.
Oh, there's a
Instead of
2
8 by
here.
5 h, isn't it?
Okay, okay. Thankfully, we found out. So this is 4 point. So yes, the answer is 4 point. Okay, so in this problem, things worked. So it should work in this one too. We are just missing out on some. Okay, I'll do the calculation and post it on course. Or maybe I will edit in this PDF, and when this is uploaded, I will upload it with the solution. That would be better, right?
Great idea, ma'am. That's enough for us.
Yeah.
Yeah. Okay. Okay,
And
then
just
any other
one,
question? Yeah.
yeah, one conceptual question. The idea of taking the unit vector to do this. I know you kind of explained it. I'm still struggling to visualize it. So the reason why we take the unit vector is to move it in that direction. Is it why do we find the unit
Yeah.
vector?
So when you mean direction, it means the unit vector along that direction. So when you mean the direction vector, that itself is a unit vector along the direction whatever we are looking at. So if I take a point, say 2 comma 0, if I tell that I want to move along this direction, it means that I am doing dot product with that direction vector, which is the unit vector along this direction. So along the direction of 2 comma 0 would be along the x-axis, but when I want to multiply it with a direction vector, I will divide it by the norm and make it 1.
Okay.
May I try it in a different manner, ma'am?
Which one?
This one.
Oh,
Sir
yeah,
asked
sure,
some
sure,
question, no?
please. Yeah,
Sir,
please.
actually, when we take the velocity and the acceleration kind of thing, if you wanted to have a rate of change of acceleration, then we'll be coming only to the velocity kind of thing. Then this direction is always there with the velocity. So we will be calculating like that if it is needed.
Okay. Yeah.
Am I something like sensing, sir, or you're something bound kind of thing?
No, I'm getting a sense of it. Yeah, I think it helps. Thanks.
Thanks, sir.
Yeah. Okay. Any other questions?
So, I mean, just maybe a foolish question. If I just didn't take the unit vector and did it on the actual vector itself, does it mean anything? If I take 2 minus 2 and 1 instead of the unit vector of 2 minus 2 and 1.
I think the magnitude would change, but because the direction is the same, it's just the magnitude that's going to be affected. But I really don't know the physics behind this, like why take the unit vector. Yeah.
And here we are calculating only the magnitude, sir. Taking off this
Only the
vector.
direction.
Yeah, direction we are keeping apart.
In this case, it's only the direction.
That's all, sir.
So how the rate of change would differ if I didn't take the unit vector means with respect to physical quantities, I don't know. We should explore.
Right.
Yeah.
Okay, ma'am. Thanks.
Or is it like you calculate, yeah, just like someone mentioned earlier, no, rate of change per unit time. So that is why it should be per unit time is what we calculate. Is it because of that or something? So we take the unit vector instead of.
In physics, normally we will be getting only three-dimensional, maximum four-dimensional. That is there in Einstein's theory, maximum. But when we are doing this vector algebra, we will be discussing with n planes and n vectors kind of thing. So conceptually, we can understand up to three-dimensional only and apply to that from to the to the nth vector. So that is the concept what I understood till now.
Yeah, we can. I was asking about 2D only. Like when I talk about velocity, so when I move, say I take the derivative. Let's take. Okay, the derivative won't make sense. We need to look at partial derivatives. Okay, if I want to change, check the rate of change along x direction, I will do dou f by dou x, right? Oh, okay, x direction also won't make sense because it's already unit vector. Okay, so if I want to calculate the rate of change along this direction, then why did I convert this vector to a unit vector? Is it because velocity is like we calculate the rate of change per unit time or something? Is it because of that?
The answer is in your first point what you have discussed, ma'am. We can only multiply the vectors, scalars kind of thing, not the vectors. So we, whatever it might be, it is a two-dimensional, three-dimensional, n-dimensional kind of thing. All things will be everything will be having a 0, 0 and a unit vector.
Okay.
So we will concise that vector and do the scalar multiplication or the functionality what we are expected to do and multiply with the same vectors, then we will be getting the respective things, I believe.
No, I was asking about the physical interpretation. Like velocity, rate of change per unit time, is that how we usually calculate?
Velocity is per time now.
Okay, so is that per unit time? Is that why we are taking unit vectors like movement
Yes,
per
ma'am.
unit?
For why we are doing that dou square x by dou square y is also to get that acceleration is to the vector state. Scalar state kind of thing. Double thing what we are doing. Normally what it happens is in physics actually we'll be having the same kind of denominators like time or whatever it might be, but when it comes to economics kind of thing we'll be having different bases like dou x in the denominator I'm talking about, dou x, dou y, dou z, dou p, dou q, whatever it might be. N level of vectors will be there. Means, let us say, if we imagine a stock market kind of thing, n kind of things will be affecting that one. Let us say, if we identify something like five factors that is affecting that particular stock price or market kind of thing, then this partial differentiation will be very much useful for us over there to get to some numerical values or points kind of thing, critical points or whatever.
Okay. Okay.
Is there an equivalent of the unit vector in a single variable world? Or we just assume it's per unit, so and therefore we don't even have a unit vector? Like, I mean, just like how we are doing for unit vectors, in single variable we just add h. That's it. It's f of x plus h.
Yeah, it's just one, right? One is our unit.
So it's per unit of h that we are differentiating.
Yeah. 1 times h.
1 times h.
Yeah.
Okay, ma'am. Anyway, I just wanted to get down.
Very sorry to intervene, ma'am. When would you be
Okay.
uploading this PDF?
I'll try to do it by tonight. I need to sit and sort out this, and then I'll maximum by tomorrow.
Yes, ma'am. Thanks.
Ma'am, you'll be taking the morning session also, right? Would it be you or someone else?
No, Subhashish Da will be taking. Subhashish.
Okay, and then the link that you were referring, how will come to know that?
Yeah, I'll show that.
Okay.
Ma'am, will there be such live sessions at the end this term also?
At the end of?
Uh, like the previous term, will there be live sessions this time also?
Revision session, is it?
Yes, ma'am.
Yeah, we will have. I think there are 4 revision sessions. Yeah. 4 or 3, I don't remember. 4, I guess. Yeah.
3 I have seen in the calendar, ma'am.
Revision session, is it?
Yes, ma'am. On December 3rd or kind
December
of thing it is
3.
there.
Yeah. Then whatever is updated. Okay, so in this term 2 maths 2. Yeah, live sessions maths 2, week 10. This one, problem solving with open session for week 10.
34.
Yeah, so this one. It was streamed on July 3rd or 23rd this year. So in this video, he has given a beautiful interpretation. Yeah, this one.
Sure. Okay.
Okay.
Thanks, ma'am.
Thank you. Thank you very much.
Yeah, okay. I'll upload the PDF by tomorrow.
Thanks, ma'am. And whatever I have expressed are purely my expectations or my assumptions regarding this dou x by dou y kind of thing. Please check and confirm it to us, ma'am, if it is possible with you, with your team and all.
Yeah, sure.
Great, ma'am. Thank you.
Okay. Thank you.
Thank you so much.
Yeah.